And I just want to say that this talk is based on work published in JCAP with Ido Bendayan and Utkarsh Kumar, and also on work in progress, which will be the second part of this talk. So I'm going to talk about cosmology with unparticles. That will give us bounces, inflation, cyclic universe, and dark energy, hopefully. And it doesn't. So that's really weird. It doesn't move.
Is this you are in the restaurant?
Oh yeah, oh, it's working. Perfect. So starting from the basics, we do have quite a few things in the early universe that we cannot explain or understand using just GR and standard model of particle physics. And homogeneity of the early universe and some only homogeneities of the CMB are one of these things. And the other thing that we cannot really understand using the standard model of cosmology and particle physics, dark matter and dark energy, why 95% of energy density in the present day universe is of some exotic origin. And obviously, in order to solve these problems, you need new physics. You can't just have Einstein tensor and standard model energy stress tensor on the right-hand side. So you need something new in Einstein equations. And most people in this conference would add something new on the gravitational side. And obviously, this is an amazing idea, but so far, GR is an amazingly successful theory. And there are no, in my opinion, no big arguments why it should be radically modified. And then, so since then, let's try to add some new matter to the right-hand side of Einstein equations, but this time not scalar fields, because pretty much everybody adds scalars. So we will try to add new stuff on the right-hand side of Einstein equations that will solve at least some of the problems that early universe cosmology is putting in front of us. So first of all, what are these unparticles that we are going to talk about? So all of that started in 2007 by with paper by Georgi. And pretty much what you do is you start with Banks-Zaks theory of massless fermions with some gauge group. So all of that is very long and very complicated. I will make very, very short introduction to that. Pretty much what you have is you have fermions. They are coupled. You can calculate the trace of energy momentum tensor of these fermions, and the trace depends on the couplings and on beta function of running of these couplings. And then you realize that the Banks-Zaks theory of these fermions has non-trivial fixed point in infrared. And below this fixed point, well, some new physics appears. So what you do is you say, okay, in high energies, this behaves like free fermions that behaves radiation-like. You pretty much have radiation, and around this fixed infrared point, you have something new, and you can calculate the trace of energy momentum tensor and average it, and you realize that what you get from this Banks-Zaks particles is a soup of stuff that we called unparticles. And the trace of the energy momentum tensor, namely the energy density minus 3 times pressure, is a function of their temperature to some power, where delta is a parameter that comes from couplings, beta functions, and everything. And the same story with A. So we have two free parameters here, and we have temperature of these guys. So now you have energy density and pressure as a function of temperature, because you can use the first law of thermodynamics. So here we have sigma T to the fourth, which is sigma is pretty much counting the relativistic degrees of freedom. This is normal radiation term, and here is your exotic stuff that you get. Okay, so now there's what you can do is you can redefine A and delta in order to get some B in here. So whenever B is 0, you recover regular radiation. So what are the values of delta and B? And people do not agree on that. So some people say that any delta would do, and some people say that only small and positive delta are acceptable. But so far, let's assume that delta can be pretty much anything. And let's try to understand how the universe filled with unparticles evolve. But before we do that, I want to emphasize that capital T is not the temperature of radiation, it's the temperature of unparticles. So these are separate fluids with separate temperatures. Radiation behaves normally. Its energy density is T radiation to the fourth. Temperature of radiation scales like a 1 over scale factor. And in order to see how unparticles behave, you have to solve continuity equation for unparticles. And then you can actually get analytical solution analytical solution for the scale factor as a function of temperature. And what you can see is that this analytical solution can be massively simplified. So here you can see that I guess that this is covering part of the screen. So you can see that if you rescale the temperature, I will define y in a second, you can simplify the scale factor in a very massive way. And let's ask ourselves, what is the y? Before we define that, just note that clearly scale factor may have a pole in here, maybe infinite for some finite temperature. So y is T divided by Tc, where Tc is critical temperature of unparticles. And Tc is defined in here, and obviously doesn't have to make any sense, because it may happen that Tc is complex or Tc is negative, and then it cannot play a role of temperature that one could reach through the physical evolution. But let's assume that Tc is real and positive, so let's choose our parameters of the model as such, and let's assume that energy density, critical energy density at T equal Tc is positive, and then really you have a pole of a scale factor at non-zero temperature. This is quite amazing because pretty much it tells you that there is a minimal or maximal temperature of the system. So it means that you are very likely to have some constant energy density here, which is very, very useful in context of generating inflation or dark energy. And what is the other way to see that? Well, you can calculate the continuity equation for unparticles at the critical temperature and can see that time derivative of energy density of unparticles is zero at that temperature. So pretty much this is the point where you have de Sitter. How awesome. So we already have a candidate for maybe inflation or dark energy. Let's see if there are any other features of unparticles that are fun. And yes, you can make a bounce with unparticles. You can have bouncing scenarios, and so far, let's assume that the universe is only filled with unparticles, only. So then you ask yourself whether there is such a TB, temperature of the bounce, such as Hubble parameter and also energy density at this temperature is zero, and then H dot at this temperature is positive in order to have a bounce, not a recollapse. And yes, you can find such a temperature, and there's only one unique solution. Pretty much it requires beta B to be negative, and it requires delta to be between -3 and 0, including -3 and 0. Why such a values of delta? Well, because otherwise you will have a recollapse, not a bounce. So now we have a part of parameter space that can give us a bouncing solution, and we can pretty much solve the equations of motion. And the result is quite amazing, because what you have, this is the Hubble parameter as a function of time. What you have is a constant and negative Hubble parameter. So you have contracting de Sitter universe, followed by a bounce, and followed by the de Sitter expansion of the universe. And the temperature is almost constant, very close to critical temperature, then it has its minimum at the bounce, and then it's almost constant again. So it pretty much looks like deflation, bounce, inflation. But, well, this inflation is no good. Why? Because, first of all, null energy condition is violated throughout all of the evolution, and that's pretty bad. The other thing is that the temperature always keeps growing. You can never have a graceful exit since then. And the other thing is that the perturbations that you generate during such a de Sitter phase are growing outside of the horizon. So you don't have a freeze out of perturbations. So this is not a good candidate for cosmic inflation, but well, so far we use the universe filled with unparticles only. So let us go to more realistic scenario. Let us assume that the universe is actually filled with some regular matter. So let's say that we add to the picture some perfect fluid. So this guy is energy density of some perfect fluid, which with equation of state omega, like pressure equal omega times energy density. And obviously the energy density redshifts like this. So then you can ask yourself, what is the energy density as a function of temperature of unparticles? Well, you can still, even in the presence of perfect fluid, you can still solve continuity equation for unparticles. You can still obtain the same result for a scale factor as a function of temperature. And you can put the scale factor here, and you have energy density of perfect fluid as a function of temperature of unparticles. So now all of the right-hand side of the Einstein equation can be parameterized with one parameter, with the temperature of unparticles. This is pretty useful in context of calculations and, in my opinion, pretty awesome. Okay, but what are the what is the phenomenology of that, and is there any possibility of having a bouncing solution? Well, in the pure unparticle case, we had only one solution to the equation of energy density equals 0. Now you can have many solutions to that. You can have many temperatures, which gives you bounce or recollapse. But one solution is always present, this so-called T naught defined in here, where alpha is pretty much a ratio of energy density of a perfect fluid to energy density of unparticles at the moment of a bounce. Or recollapse, because actually, if you think about it, at T equal T naught, you may have a bounce or a recollapse, and you may have a minimum of temperature in here or a maximum of temperature in here. So altogether, you have 4 options at this very point. So let's start our evolution of the universe at this temperature, T equal T naught, and let's see what kind of possible scenarios for the universe one may find depending on parameters of the model. So just for simplicity, let's fix alpha to be 1. So let's energy density in the particles contribute equally to the energy density of the universe at the moment of a bounce. And let's ask ourselves what are the possible scenarios for the evolution of the universe. So whenever there is red, here there is a plot which shows you possible cosmic scenarios as a function of equation of state of the fluid and as a function of this delta parameter for unparticles. So what you do is you always start at the T equal T naught, where you know for a fact that there is a bounce or recollapse. Whenever there's green or yellow, there is a bounce. Whenever there is a red and a brown, there is a recollapse at this point. What are the most essential scenarios? Well, first of all, everything can go wrong. So you can start at the recollapse and your universe can recollapse immediately to some Planckian energy density and it can reach singularity in no time. So that happens whenever you are in region 2, 3, or 5. So you can see that the big chunk of this parameter space is actually horrible universe that could never exist. You start and it collapses itself in a fraction of a second. And then the most intuitive, the simplest case is the region number 4, which is just a regular bounce that we all know and like. So this is the Hubble parameter, the orange line. You can see that when you have a bounce, when Hubble parameter crosses 0, it reaches its maximum and then it decreases while the universe grows. So this is a normal bounce, just like in, for instance, loop quantum gravity that some of you guys know. And here this X is temperature divided by the temperature at the moment of the bounce. So you can see it has a maximum at the bounce. It has a temperature has a maximum at the minimal volume of the universe. Well, this is pretty intuitive. So this is the bounce that we all know and like, but there are some other crazy stories in here. So for instance, let's say that we are in region 1. It doesn't matter whether you have a recollapse or a bounce at T equal T naught. In region 1, you always obtain a cyclic universe. As I told you, some people believe that small values of positive in such a theory. So let us consider small and positive delta. And you have a cyclic universe with cycles that can be quite long. Here we present relatively big delta still, only because the numerics were very heavy. But if you think about it, if you increase delta just like twice or 3 times, your universe becomes huge and the time distance between bounces becomes very realistic. So pretty much without much of the fine-tuning on delta, you can have a very realistic universe. Here filled with a universe which is and has a time of cycle longer than the age of the universe. And then you can have a very non-realistic, unrealistic cyclic solutions. So let's say that we are in the region 6 in yellow or brown. This guy means that you start with a bounce. This guy means that you start with a recollapse, which doesn't matter. It's all the cyclic universe. What's crazy about this model is that at the moment of the bounce, at the minimal volume of the of the minimal value of the volume of the universe, the temperature is also minimal. And when you grow, the temperature is, when the universe grows, the temperature is growing as well. So this is rather counterintuitive. And furthermore, the maximal value of the temperature is not very different than minimal value of the temperature in such a model. Bounces and recollapses here are very shallow, and the universe don't have enough time to grow. Highly not realistic. So these guys highly not realistic. This guys collapse immediately. This guy collapse immediately. This guy is a de Sitter bounce that we talked about. This guy is a normal bounce, and these guys are relatively realistic. So in fact, not a huge part of parameter space gives you a scenario which is very realistic, but still you can have a realistic cyclic universe or realistic bouncing universe from that. Okay, so what are the conclusions about the cyclic and bouncing part? First of all, if you assume that unparticles are the only guy which fills the universe, or if you assume that there are unparticles in perfect fluid, in both cases you may have a bouncing solution for the universe. And for unparticles only, the only bounce is the so-called de Sitter bounce, when you have a bounce and then the de Sitter expansion of the universe, which never ends. And for unparticles and regular matter, regular perfect fluid, you may have a normal bounce, de Sitter bounce, realistic, not realistic cyclic universe, but unfortunately you may have quite a few cases which are really drastic, which leads to collapse of the universe. Are there any questions to the cyclic part? No? Let me go to the dark energy part. So sorry guys, I have some technical issue. Okay, so we already mentioned that unparticles have this exotic feature that at the critical temperature their energy density is constant. So pretty much they can be used to generate dark energy. But let's understand, what does it really mean that a scale factor has a pole for unparticles? Well, a pole of a scale factor in terms of temperature is nothing really exotic. If you think about regular radiation behaves like 1 over temperature. So when scale factor goes to infinity, the temperature goes to 0. So it also has a pole. It has a pole at 0 temperature, and you really never reach it. Yeah, your universe keeps expanding and expanding, and you never reach temperature equals 0. Well, the same story about unparticles. You always go towards critical temperature, but you never really reach it. So T equal Tc is your future infinity of your evolution. Is the point where the universe obtains infinite volume. Okay, but does it mean that, what does it mean in context of the evolution of the temperature? Well, it means that the range of allowed temperatures is divided into 2 fractions. You can either have a temperature smaller than Tc or bigger than Tc, but you can never cross critical temperature. It means that either you may have a bouncing scenario when critical temperature is a maximal temperature of the universe, or you may have a dark energy scenario where the critical temperature is a minimal temperature of the universe. And obviously we want to focus on the latter case. What are the conditions for the dark energy? Obviously we want Tc and ρc to be positive. We also demand that throughout all of the evolution of the universe, the derivative of a scale factor with respect to temperature will never be 0. And this is very important because otherwise your evolution goes nuts and pretty much the solution collapses. So your temperature must always either increase or decrease, but in our case, in the case of dark energy, the temperature must always decrease throughout the whole evolution of the universe. And since you don't want null energy condition to be violated, you require delta to be between -3 and 0. Okay, we have few conditions for the dark energy, and let's see if it works. So pretty much you can divide your evolution of the universe into early universe and late universe. So as I told you, if you think about the unparticles in early universe, they behave radiation-like. They pretty much behave like a bunch of relativistic particles. So you can see that the energy density of unparticles is just T to the fourth, where T is some temperature of this relativistic fermions. But whenever you decrease the temperature of unparticles, whenever you grow the volume of the universe, you should reach the range when the temperature becomes of order of critical temperature, becomes of order of its minimum value. And then you can actually, in this regime, you can solve the system analytically. So here we assume that the universe is filled with some radiation, with some dust, and with our unparticles, and we solve analytically equations of motion for unparticles, assuming that unparticles have temperature relatively close to their minimal temperature. What happens, what's important, there are many coefficients here that completely don't matter. What's important here is that energy density of unparticles behave like a constant, and there is a correction which behaves like an inverse volume. So n is the number of e-folds, so e to minus 3n is like 1 over volume of the universe. And here is the equation of state of unparticles, which is -1 plus some correction, which is suppressed by the volume of the universe. So if you wait long enough, your equation of state will go towards equation of state of dark energy. And what's really interesting is that your unparticles behave like constant part, which is pretty much dark energy-like, and the part which behaves like dust. So our hope was that such a model could contain both dark matter and dark energy. Namely, the constant term could be dark energy, and this term could be dark matter. Unfortunately, what happens is you have to satisfy the BBN constraints, the Big Bang nucleosynthesis constraints, and they do not allow too much of the exotic matter around 1 MeV. So whenever you want to fit to these constraints, you have to assume that all of this guy is very small, where Y0 is the ratio of present day value of the temperature of unparticles divided by critical temperature. So pretty much you have to assume that Y0 is extremely close to 1 in order to have a realistic evolution of the universe. This assumption seems to be nuts, but it's not really that crazy, because if you think about it, temperature naturally wants to be of order of critical temperature, and it's strongly any time-dependent term is strongly suppressed by the volume of the universe. Okay. Oh, so this plot looks nuts. I'm very sorry for the quality of that. But here I just wanted to show you how the evolution of the energy density of radiation, dust, and particles looks like. And I wanted to show you that unparticles behave radiation-like. So their ratio to radiation is constant. And then they behave like dark energy and they dominate the universe. Okay, thank you very much.
Thank you, Michał. Let's thank the speaker for the very nice talk. Are there any questions, comments? Michał, I have a simple question. What is the leading physical motivation behind the unparticles? Could you
you mean at the level of particle physics?
Yeah.
Yeah, so the thing is that there's a very broad, so there's quite an old idea of this Bank-Zaks that there is a fixed IR point of these fermionic theories. So pretty much this is the very basis of that. And the idea wasn't even ours. So this was all developed by Georgi and then by Grzadkowski and Wudka later on in like mid-2000s. And pretty much if you play around this IR fixed point, you get all of the basic phenomenology of unparticles. What we did is we simply employed the cosmology we employed the tools of pretty much Friedmann-Robertson-Walker metric, and we solved the equations. But yeah, the idea is pretty old. It's just that the theories with fixed IR point, they developed effective field theory in lower energies, in lower scales that may behave nuts.
And then from that consideration, can we learn something, and can we infer something about physical properties of unparticles?
Oh, I mean, definitely. For instance, that they can freeze their energy density. That's for sure. The problem is we are trying to look for a smoking gun, but the problem is that so far everything looks like lambda CDM, pretty much. So for us so far, it's rather hard to see, experimentally, how unparticles would be radically different from other models of dark energy.
From what I remember, somehow the unparticles are considered to be scale invariant. Is that correct?
I mean, so unparticles are, in this sense, not scale invariant, but they strongly depend on the scale of a cutoff.
Mm-hmm.
So you have this cutoff scale above which they depend completely different and below which they behave completely different. In this sense, yeah, there is a very strong scale dependence. So what we have to assume is that we are always below the scale, that we are always safe, kind of. But there is no fundamental scaling there, so it can be very far away.
Okay, Michał, thank you once again for the very nice talk.